There were 5 conditions or assumptions, if you want to think of them that way, that make simple linear regression valid, or that make the t-test for simple linear regression valid. The first 2 are easy to check. The first one was that we had a random sample. The second was that we had a quantitative response and quantitative explanatory variable. So the first one we check just by thinking about, well, how did we collect our data? Did we use a random sampling process, or did we use some other justifiably unbiased sampling method where we were pretty sure that our data are going to be representative of the population at large? The second one, we just identify what the 2 variables are that we're using in our analysis and make sure that it's reasonable and justifiable to take an average of them. So just having numerical values we know is not enough to make data quantitative. Talking about averages also must be reasonable. So zip codes are numeric but not quantitative, but height is numerical and quantitative as examples. So, in addition to randomization and quantitative response and quantitative explanatory variables, we also have to make sure that we have a linear model be reasonable in the population, such as mu y equals alpha plus beta x, or we can talk about y equals alpha plus beta x plus random error. So we can either be talking about the true mean response at each value x, or we can talk about the individual's response at each value x. We also have to have that the population values of y at each value of x follow a normal distribution with the same standard deviation. So we're finally going to talk about how to check these 2 assumptions. This first one, the relationship is linear, we check this using a scatter plot of y versus x. So that first scatter plot we check at the very beginning when we're looking at our data, we're identifying the form, the shape, the direction, the form, the strength, the direction, and whether there are any anomalies present. That's where we're making sure that a linear relationship is reasonable. We never truly know what's going on in the population, so that's why this random sample, this representative sample, is a really key assumption. Because if we have an unrepresentative sample, it doesn't matter what that sample looks like. If it's linear but not representative, then we have no basis for justifying what's going on in the population. So we typically look at residual plots to justify the other two conditions. So we really have 2 conditions stacked into one here. They're both about the population distribution, but one is about the shape of the distribution, and one is about the standard deviation at different values of x. So we use several types of residual plots. So here I've got a residual plot, and this would be a residual against the explanatory variable. And this would be section 13.4 in the notebook, but also section 12.4 as well. And in this plot, we have, say, residual versus car weight. Or we might have residual versus age of a person. Or we might have residuals versus volume, right? No matter what, this would be our x variable, and we're plotting our residuals against them. In this case, what we want to see is that the spread, that is, the variability around the line at all values of x, is the same. And so we can see that not all residuals are the same size, but that the typical width of the plot is the same. This first plot looks good. So the spread here looks fantastic. This last plot, we can see a very narrow width at the beginning, a wider width in the middle, and a very large width at the end. So if I were to draw an outline, we can see that the shape looks kind of like a funnel. So in this case, the spread is not constant. We've got what is known as a funnel, or we might say a cone shape. So if we're thinking about this little bit of variability and then increasing variability as it goes out like that, that's problematic. This first one, spread is the same. So you want parallel lines drawn around the upper and lower bounds, so to speak, of your residuals. This middle one, the spread, is about the same. So if I'm looking at the spread here, the spread here, the spread here, the spread here, that's pretty constant. So I'm not too worried about the spread. So the spread, or the standard deviation, is okay. The problem here is this is nonlinear. There's a clear association. So that means maybe the linear model isn't appropriate. But we would have picked this up in our scatter plot. For something like that to happen, to get this kind of plot, if this is my x, so this is age, and this is my y, here's my prediction equation. My data would look like this around my plot. So I would have already seen in a simple regression equation, or simple regression scenario, I would have already seen that nonlinearity. However, in a multiple regression scenario, I might not pick that up. So this is problematic. So if I see something like this, where I've got a shape or a curve, if I've got a curve or an association in my data after I've plotted my residuals, I need to investigate my model. I'm probably missing a variable. I don't know which variable, but there's probably another variable that can help pick up some of that association. What else do I like about these plots? Well, the thing I like about this first plot is that this looks like just a random pattern. There is no association. So this first plot checks all the boxes. I don't see any shape, so there's no cone or funnel, and I don't see any association or pattern. So as x increases, the residuals aren't increasing, there's no curvature. So this is lovely. If we think back, so these are for our midterm elections data. We have our residuals versus our predictors. How do you think we feel about this? Well, the upper bound for our residuals and the lower bound for the residuals, I don't see any real cone or funnel. I can draw pretty much a parallel line there, so it looks like I have a constant standard deviation. No matter where I'm predicting, the width of my residuals is about the same. So that is good. Additionally, I don't see anything like I had in that second plot up there. I don't see any association, no pattern or trend. So the linearity of my model seems like a reasonable assumption. So it looks like I've satisfied those two basic assumptions. Now what I haven't checked yet is my normality. I cannot check normality with a scatter plot. What I do need is a histogram. So if you're giving a histogram of my residuals, you better be checking your normality. Similarly, if you have a histogram, you can't be checking the standard deviation or the linearity. So scatter plots are for linearity and standard deviation. Histograms are for normality only. In this case, I have the same data. So this is my midterm elections data again. What I've done is I have my histogram at the end of my residuals versus predicteds. So this is residuals versus y hat. What I want to see, what I would love to see, is a unimodal and symmetric distribution, which I don't quite have. This is actually left skewed. But T procedures, especially two-tailed tests, are said to be robust to small departures from normality. So based on this histogram, I would not say that these are normal. This does not look like I've pulled a sample from a normal population. But it's not so severe that I am worried. If I had something that looked like the F distribution I drew in the previous video, I would be worried. So what's a severe departure? A severe departure would be something like that. So that would be severe skewness. Severe departure would be something like that. So something that's clearly not normal. Here we only have 27 observations. So we could just chalk it up to imperfections in a small sample, right? It's not grossly non-normal. I don't love it, but we should be protected. Assuming we've satisfied our conditions, that our inference is reasonable, there's one more thing we can do when we look at the data around the line. And that is by looking at predictions and the response. The inference that we've done so far is inference for the slope. And so I'll remind ourselves that we have looked at beta equals 0 versus generally beta not equal to 0. But we can also do beta less than 0 or beta greater than 0. So we can do one or two tailed tests for that alternative depending on if we're doing a T or an F test. But what if we want to know about the response? So what if we were trying to come up with inference for the mean response? So the true average mileage for cars that weigh 1,500 pounds. Or if we want to know the true average change in the percent change in house, or the true average percent change in house seats when unemployment is 3.5%. That's a different question. And to do that, we're going to have to use intervals to predict our response. There are two kinds of intervals, and it depends on the kind of question we're asking. A confidence interval gives us an interval for the mean response, and that would be the true mean response at a predicted value of x. The two examples I just gave, the true mean mileage for cars that weigh 1,500 pounds, and the true mean change in house seats when there's 3% unemployment, would be answered with a confidence interval. A confidence interval is the same form of all confidence intervals we've seen so far. We have a statistic, in this case, that would be our predicted response. We're still going to use a t-star critical value with n minus 2 degrees of freedom, and the standard error of y hat. The standard error of y hat is going to be estimated using s over square root of n, but if you remember from our previous video, we estimate s with RMSE. That is the variability of our observations around the line. This is a great prediction, a great estimation when we're predicting right at the mean of x bar. It gets worse when we get farther away from the mean of x bar. The other kind of interval we can do is to predict for a new or an individual response at a particular x value. Our prediction interval is approximately y hat, so this is our statistic, plus or minus t star, and that still has n minus 2 degrees of freedom, times s, where s is still our RMSE, which is again the variability of the observations around the line. Our approximation, just like before, is less valid when we predicted values very different from x bar. So, our confidence interval should capture the true regression line in the population. because we're trying to predict or capture the true mean response, and the regression line is the true predicted mean response at all values of x. Our prediction interval, on the other hand, should capture most individuals who have that value of x. So there are two different goals. One is trying to capture the true mean response at that value of x, so that would be the regression line or the true regression equation. The other is trying to capture the most individuals who have a specific value of x. So one is looking at a population parameter, the other is looking at capturing the most individuals of that population. Like other intervals, manipulating certain things will cause these intervals to get narrower or wider. So for example, as the sample size that we collect our data or base our intervals on, so as n, that sample size increases, the intervals get narrower. But as we can see from the formulas, it's going to be very clear that it gets narrower for the confidence interval, but less obviously so for the prediction interval. So the confidence interval gets narrower faster. The prediction interval less so. Also, we can think about what happens when there's more or less variability around the line. So when r squared is large, so close to 1, that means our residuals are small. That means there's not a lot of unexplained variability. And we also know that that means our RMSE is small. There's not a lot of variability in our residuals. So that means that both the PI and the CI are narrower. But we can see from these two approximations that the PI always has a bigger standard error than the CI. The CI has a standard error of S over the square root of n. The PI has a standard error of S. So no matter what, the PI is going to be wider. And that's what's illustrated here. So here are our car weight and mileage data plotted again. The red line, this is our y hat equation. The dotted bands, this is our confidence interval. And you can see it gets really narrow in the middle and really wide at the extreme. So the farther away I am from the sample mean weight of cars, the less precise, the less accurate that interval gets. Or the less precise my interval gets. The same is true for my prediction interval. The shaded region, this is my prediction interval. It's a lot wider than my confidence interval. So my prediction interval is trying to capture 95% of all individuals in the population at a specific value. So it's got to be wider because individuals are more variable. So right here we can see that even at the sample mean weight, the prediction interval is wider. And it gets wider and wider still. It's completely off the screen at more extreme values of x.